Bismillahirrahmanirrahim. I'm Engineer Maham Misbah and I'm going to present the paper titled TFNet Deep Learning Empowered Tiny Feature Network for Nighttime UAV Detection. Among other authors are Engineer Misha Urooj Khan, Dr. Zhaohui Yang and Dr. Zeeshan Kaleem. The table of contents which will be covered in this presentation: motivation and introduction, literature review, proposed TFNet, dataset and implementation, results and discussion, conclusion and references. Moving to the first part, motivation and introduction. Technological advancements have normalized the usage of unmanned aerial vehicles or drones in almost every sector spanning from military to commercial. Currently, the commercial and military industries that rely on UAVs are expanding rapidly, attracting investors who are driving improvements in drone technology and continuously trying to reduce the size, weight, and prices. However, they also pose serious security concerns due to their enhanced functionalities and easy access to private and highly secured areas. The worldwide terrorism problem has expanded this domain into the areas of individual security, border control, national security, and military surveillance. Several instances related to UAVs have raised security concerns leading to UAV detection research studies. Therefore, real-time drone identification and detection is urgently needed to shield high-security places from the risk of drone intrusion. A lot of research has been conducted to date for the UV detection using visual, radio frequency, acoustic, thermal, and radar methods. Visual-based UV detection techniques offer a reliable solution compared to acoustic and radar-based techniques. However, visual techniques perform poorly at night in complex backgrounds and in adverse weather conditions. Therefore, a robust night vision-based drone detection system is required to efficiently tackle this problem. Development of infrared-based object detection and classification are among the fastest topics being worked on. Currently, convolutional neural networks are the most effective models for detecting objects. AlexNet's groundbreaking performance in the 2012 ImageNet Large-Scale Visual Recognition Challenge marked a turning point for the image recognition. Among some other frameworks for object detection are Labeled Regions CNN, RCNN, Fast RCNN, and the Faster RCNN. In contrast to these region-based algorithms, you only look once YOLO is an efficient object detection approach. It works by predicting the presence of an atom and its bounding box for a fixed size grid that tiles the input picture. It is a single-stage detector, which means it requires a single run through the network for detection. The figure shows the overview of YOLO version 5. The use of infrared cameras for nighttime monitoring has become quite common due to the use of night vision technology in surveillance and protection. Therefore, we considered IR-based drone detection technique in this paper. Detection methods considering IR images is hindered by the scarcity of large datasets and the expensive cost of an IR camera. In the proposed framework to efficiently detect UAVs during nighttime, we employ UAV detection based on IR images. We considered a dataset consisted of IR-based UAV images with multiple complex environmental background and weather conditions. We proposed TFNet, an improved version of YOLO V5S, by introducing kernel-based modifications in the neck and backbone. For a fair comparison, we trained all considered models with same dataset, learning rate, warm-up setup, and epochs with early stopping. Moving on to the next section, literature review. UAVs have grown in popularity for a wide range of uses. Many incidents involving the illegal use of UAVs is making it difficult to regulate them and mitigate the associated privacy risks. Currently, there are two major challenges to drone identification in real time. One of them is the rapid speed with which drones move, which calls for equally rapid detection systems. Secondly, multiple sizes of drones further complicate the detection process. Authors in one used CNN spot vector machines and k-nearest neighbor to train a drone bird dataset and achieved a maximum accuracy of 93%. The study in 2 reduced the size of YOLO V4's convolutional channels and shortcut layers and improved the accuracy of small drone detection. 10,000 drone images were captured with OnePlus phone camera. Results showed that improved YOLO v5 model achieved 90.5% MAP. A novel approach for detecting multi-rotor drones was presented in 3. They replaced the YOLO v5 backbone with efficient light, which allowed them to streamline the model by eliminating unnecessary parameters. To speed up network convergence, an angle limitation was added to the existing regression loss function. They trained and validated the model using a dataset of 1259 multi-rotor UAV images. The modified YOLO v5 displayed enhanced detection performance in terms of precision, recall, and MAP. The study involved fine-tuned YOLO v5 model on a publicly accessible dataset of 1359 images. They also performed data augmentation to overcome the missing data points. The proposed model yielded an accuracy of 95.2%. The work in 5 considered object recognition and classification at sea surface using thermal and infrared images, and they yielded an accuracy of 92.5%. TinyFeatureNet. PostDFNet has 4 blocks: input, backbone, neck, and head. To facilitate speedy inference with no MAP cost, the input block maps spatial information from the input imagery to the channel dimension. It also performs data preparation by using mosaic data augmentation and adaptive image filling techniques. Training time and the need for a tiny mini batch size is reduced due to MDA's ability to teach the DFNet object identification on a lesser scale than conventional object detection methods. The cross-stage partial network (CSP) and spatial pyramid pooling (SPP) are used by a backbone block to extract the feature maps of varying sizes from input images. And inference times were further reduced by using the bottleneck CSP block. For precise detection, SPP helped the extraction of feature maps at 3 different scales. Feature pyramid network (FPN) is used in the neck block, which captures semantic attributes from the highest to the lowest levels of the hierarchy. The final detection is provided by the last head block. Anchor boxes are a set of bounding boxes that have been labeled in terms of their height and width. In TFNet, we used 8x8 P3, 16x16 P4, and 32x32 P5 anchor boxes for the identification of target objects. The figure shows the architecture of the proposed DFNet. Is dataset and implementation. A dataset with more than 3000 IR images of UAVs flying at night in various backgrounds. We set the train test ratio to 8:2 with 3100 training and 791 test images. Dataset visualization shown in the figure depicts the multi-size UAV's target. In pre-processing step, we resized the images to a fixed size of 416 x 416 and performed contrast enhancement before training. Here the table shows the hyperparameter qualitative analysis. We used an input of 416 x 416 and trained on 300 epochs with 232 layers. We used a learning rate of 0.01, momentum of 0.937 and a weight decay of 0.0005. All the models are trained on Google Colab with K80 GPU and 12 GB RAM. During training, the objectness loss decreased from 0.019 to 0.014 and object loss decreased from 0.09 to 0.04. The precision, recall, MAP, and IOU over 100 plus epochs shows an increasing trend. Moving on to the results and discussion. Assess the performance of the proposed DFNet and YOLO v5 small, medium, large, and nano by calculating true positive, true negative, false positive, false negative, precision, recall, mean accuracy, precision, MAP, and intersection over union IOU. Considering the model depth, YOLO v5 large has a depth multiple of 1 and a width multiple of 1, which makes it a deepest model, and it is with the highest computational complexity. YOLO v5 medium shows 0.67 depth multiple and 0.75 width multiple. YOLO v5S and TFNet have 0.33 depth multiple with a width multiple of 0.50. YOLO v5 Nano is the lightest model, having 0.33 depth multiple and a 0.25 of width multiple. The results indicated that YOLO v5S and TFNet showed better performance compared to both YOLO v5 Large and Nano. Shows the graphical representation of merged dataset for all 5 models. YOLO V5 small, medium, large, nano, and TFNet. Here we plotted precision, recall, MAP, and IOU over 200 epochs. The table here shows the training evaluation matrix for TFNet and 4 other YOLO variants. The proposed TFNet outperforms all the YOLO V5 models in terms of precision, MAP, and IOU. TFNet secured 95.7% precision, 84% MAP, and 44.8% IOU. In terms of recall, YOLO V5 small performed well by achieving 78.4%, which is 1% higher than TFNet. True positive and false negative, YOLO V5 medium has a highest true positive of 83%, which is 1% higher than our proposed model, and 17% of false negative. Shows that TFNet has higher sensitivity for detecting multi-size objects compared to the rest of the standard YOLO V5 models during nighttime. Mean accuracy precision MAP value compares the ground truth bounding box to the detected box and returns a score. The higher MAP score of TFNet shows its ability for accurate detection. The precision recall curves shown in the figure give the values of MAP 0.5. The precision recall curve achieved the highest MAP of 84% for TFNet. Comparatively lower MAP is achieved by YOLO V5S, ML, and N. Impact of varying environmental background on detection performance, we compare the result of the proposed TFNet with YOLO V5 models with respect to different backgrounds including clear sky, urban, dense, cloudy, indoor settings, foggy, shrub, and at low altitude, as shown in the figure. TFNet achieved 93% accuracy in urban background compared to the YOLO V5 small. Similarly, for dense, cloudy, and indoor settings, the TFNet performed well with 88% and 91% accuracy respectively. For foggy background, TFNet yielded 4% better accuracy than YOLO V5 models. The TFNet also performed better by achieving 13% and 3% higher accuracy in case of shrubs and low altitude UAVs respectively. Therefore, TFNet is proved to be a better choice for UAV detection in all backgrounds and altitudes. Kernel size enables the proposed TFNet network to perform well on multi-size images. Figure shows multi-size UAV detection by TFNet and other YOLO V5 models. Despite being lightweight, TFNet efficiently detected small, medium, and large UAVs with a detection accuracy of 90, 91, and 91% respectively. The table here shows the computational complexity of the different models. TFNet has the most comparable computational complexity with good G-flop performance of 75.2, low trained model size of 10.8 MB with 232 layers and high precision of 95.7%. Inference time and speed is shown by the table 4. TFNet achieved 0.7 millisecond NMS per image with 98 FPS trained on Tesla T4 GPU. This shows the effectiveness of TFNet model in real-time scenarios for fast UAV detection. Results with the state-of-the-art models for UAV detection based on YOLO V4 and V5 models. It is apparent from the table 5 that TFNet performed well in terms of precision, FPS, and model size compared to the other literature models. TFNet outperformed all other models and achieved 95.7% precision when compared to the 2, 6, and 7. TFNet has the highest FPS of 98. TFNet also proved to be lightweight with trained model size of 10 MB and 5.2 million parameters. Therefore, we implemented a night vision UAV detection utilizes the proposed TFNet model with IR images and achieved superior results compared to the literature and baseline models. Conclusion. We provided an improved version of YOLO V5 based object detection model TFNet to improve UAV detection in adverse weather conditions at night. Input image were adaptively enhanced to obtain better detection performance. Further, kernel-based feature map extraction was used along with the best suited hyperparameters to extract weather-specific target information for the TFNet detector. The proposed TFNet model performed well in terms of precision, model size, MAP, IOU, and G-flops compared to the baseline YOLO V5 models. The TFNet achieved 4.5% higher precision compared to the baseline YOLO V5 models and others. Thank you.